Welcome to today's webinar, Unlocking the Hidden Benefits of Ultra-Low THD Inverter in Solar and Storage Projects. I'm Oyane Gonzalez-Mendivil, PV Product Manager at Gamesa Electric. We are delighted to be hosting this event from the heart of Gamesa Electric Inverters Factory in San Fernando de Henares, Madrid, Spain. In fact, we have here behind us one of our produced inverters as a perfect background for this session. It's an exciting time for renewable energy industry as we face the great challenge of transitioning from a grid based on synchronous generators to other based on asynchronous generation sources managed by inverters and converters. It is estimated that by 2030, 1,675,000 inverters for distributed renewable generation will be connected to electricity grids all around the world. But there is one element associated with this equipment that is often overlooked and is the key to a stable grid: harmonics. As we all know, inverters play a crucial role converting the direct current from solar panels and batteries into AC current to be fed into the grid. However, the introduction of Total Harmonic Distortion or THD by these inverters can be highly detrimental for the grid in general. That's why it's essential that inverters are designed to achieve an ultra-low THD not only to avoid the losses in generation plants, but also to avoid reliability problems in other elements. Gamesa Electric has recently published the white paper titled Unlocking the Hidden Benefits of Ultra-Low THD Inverters in Solar and Storage Projects, which gives the keys to minimize the potential problems that harmonic can cause. This white paper can be downloaded from our website. To review the document in depth, we have a fantastic lineup of speakers who will dive into the THD and how the ultra-low THD of inverters like Gamesa Electric produce can unlock substantial benefits. Let's get started by introducing our participants. First, we have our Global Sales Manager, Enrique de la Cruz. Enrique, welcome. Next, we have our electric expert, Juan Armendari, Head of Electrical Development at Gamesa Electric, who has an extensive experience in the field of power electronics. Hello, Juan, and welcome. Enrique, for those who don't know Gamesa Electric, could you please give us a brief overview of the company and its products?
Hello, everybody. Before we get started with the technical content of the webinar, I want to introduce our company, Gamesa Electric. Gamesa Electric is a subsidiary of Siemens Gamesa. Siemens Gamesa, as probably everybody knows, is one of the leaders in the world in the manufacturing and the selling in the world of wind turbines. We have more than 138 megawatt already installed in the market, and we have sales offices in more than 90 countries with more than 90,000 employees. Also interesting to know that Siemens Gamesa is part of the Siemens Energy conglomerate of companies, and that provides us with a very strong footprint in the marketplace in the renewable energy. Few more details about Gamesa Electric. Gamesa Electric is, as I said before, a subsidiary of Siemens Gamesa. We have two different core technologies. We have rotating machines, we have power electronics, and overall our number of employees is about 900 today in the world, split in 7 different factories. The footprint today in both key technologies, wind and PV, as you can see in the slide, is about 8.5 gigawatt already installed in different countries in the world for PV and storage inverters. And in wind turbines, in wind converters, so our reference is close to 60 gigawatt. As I said before, we have 7 factories. We have 3 in Spain, we have 2 in China, 2 in India, and then sales offices in 2 of our more important markets, which is Australia and the US. A few words about the portfolio of products we sell into the marketplace, and we are focusing on PV and storage. We have our Proteus inverter, as you can see on the left part of the slide. Proteus, we have the PV and the PCS version for battery storage. It's a 4.7 megawatt building block, the highest power in the world as of today, and we can combine this inverter even with 2 inverters back to back in a power station, providing to the customers with a complete plug and play solution, inverters, transformers, and all the medium voltage elements. And finally, we have our orchestra, which is the power controller, is the one that we need in order to control the flow of power, the reactive and the active power in our product, in our solutions. Before we start with the details of the webinar, just 2 minutes to talk about the key features of Proteus. I already mentioned that the power is the highest in the world, 4.7 megawatt per unit. This allows our customers to design their power plant with the lower possible capex. By having the highest power, we can reduce the number of power blocks in a power plant, and that reduces construction costs, that reduces installation of cabling, cranes, and everything associated to construction. The second element, and probably the most important one, and is going to be the key discussion today in the presentation, is our highest production. The highest production of our converter is a key element of LCOE. It's basically due to two key facts. Number one is efficiency. Efficiency is something that it can be very easily measured, very easily demonstrated, because there are certificates, because there are tools in the market in order for customers to estimate the impact of efficiency in their plant. And the second one is the THD. This is the core of the presentation today. THD, or Gamesa Electric Proteus, is the lowest in the market. I will leave my colleague Jonai to explain this more in detail, and we will finalize the webinar explaining what does it mean in terms of money, in terms of energy improvement because of the THD. And finally, reliability is a key element in any power plant, and Proteus is able to provide with the highest possible reliability today based on the design, internal design, based on the water cooling combining with air cooling, so that we can reduce the stress of the key elements of the inverters.
Thank you, Enrique. Now let's hear from our expert Jonai, who will dive into the details of the white paper.
In the past, the grid was just fed by big synchronous rotating generators. The rise of renewable energies and the power electronics are changing the waveforms are carried by the grid. Nowadays, harmonic distortion is becoming more and more present and important in the grid with high renewable power sources penetration. So then, what is THDI, or harmonic distortion? The PV inverters are transforming DC to AC current. It uses power semiconductors through the pulse width modulation technique to generate AC current, thus generating imperfections in the waveforms they are feeding to the grid. Imperfections are referred as harmonics, which are quantified in the percentage value known as total harmonic distortion. So, what is the total harmonic distortion? To understand the total harmonic distortion, we need to understand what is a harmonic. Perhaps you might remember from your days in the university what does mean the Fourier transformation. The Fourier transformation is a way to represent every single signal by means of a series of different signals with different frequencies. Then you have, in every single term of the sum, you have different frequencies going higher and higher. Then, the harmonic distortion is the representation of how good is the signal compared to its fundamental signal at 50 or 60 Hertz. Then, again, the harmonics are the one defining these orders. So you have harmonic number 2, that is 50 Hertz, harmonic number 3, 150 Hertz, and so up to harmonic number 50th, which is 2,500 Hertz. Okay? Then, again, the total harmonic distortion is a magnitude that quantifies how big is the perturbation of the signal compared to a pure sinusoidal signal. Then, the THD is a coefficient between the harmonics and the fundamental. Harmonic distortion. How big or how are the effects of the THD on solar plants? Basically, we have three main effects on the solar plant by means of the total harmonic distortion. We'll have increase on the electrical losses. We will suffer poor performance of the solar plant, and we will shorten the service life of the components in the transformer that I installed there. We will suffer an increase of the electrical losses by means of ohmic losses proportional to the square of the current multiplied by the resistance. And then there we will see an affection of the THD. Moreover, we will have problems or more electrical losses in the capacitors and transformers depending on the frequency. And then we will have also a skin effect that will decrease the equivalent section of the conductors due to the fact that the current at high frequency only flows through the surface of the conductor. The second key effect is a poorer performance of the solar plant. A high THD will worsen the power factor, and we will need more apparent power for the same active power. And also, it is likely to happen malfunction in the electronic devices due to the flicker. The third problem is the shortened life of the transformers. The transformers are a big equipment inside of the solar power plant, and they will suffer mechanical vibration beyond their limits because of this high THD, and also resonance in the grid can occur because of THD. Well, now let's talk about the effects of the harmonic distortion in terms of produced energy, and now we will introduce how the harmonics are mitigated. So basically, the harmonics are producing heats in the transformers. Moreover, they are hitting the cables and they are hitting every ohmic loads. So we expect to have less energy produced in the point of interconnection rather than the energy produced by the inverters. On the other hand, we have to notice that the way the plants are mitigating the harmonics is because they are big low-pass filters. And then the harmonic current is attenuated by the PV plant. On top of that, in the case of our Proteus double power station with multiple inverters, we have the technique of phase shifting technique that allows to cancel harmonics in each other. We have already talked about the theory of the harmonics. Now, I suggest to start speaking about the standardization. The standardization bodies are aware of the importance of the harmonics. In their standards, they establish limits on the permitted harmonics to be introduced in the power grids by the power sources. So, the different bodies, they establish different grid fair standards, such as IEEE, IEC, they have their own standards. On top of that, some countries, they have their own grid codes establishing the limits of the THD. But what are defining the standards? Sometimes the technology goes a little beyond the standards. For this particular case, the switching frequency of the inverters are higher than the measured limits established by the standard. So solar inverters can fulfill the standards having a poor THD. Why we say that? We can say that because the standards are limiting the distortion up to the harmonic 50th. So 2500 Hz in a 50 Hz grid. There's no requirement above this value. The switching frequency is one of the most visible in the harmonic spectrum. But the modern PV inverters commute at frequencies far above 2500 Hz. THDI specified inverter datasheet does not consider frequencies above 2500 Hz, and usually they state THDI below 3%. What are the consequences of this lower frequency? Could mean that we have a big presence of harmonics at frequencies beyond this 2500 Hz. The presence of losses is not considered during the plant design, neither by PBSC's simulation software. Inverter manufacturers don't show information regarding to high frequency components. The impact of that is that there's a reduction in the total revenue due to the low effective current passing through the energy meter. So, what is the solution for that? The solution for that is having an ultra-low THDI design. How will we do it? Okay, our inverters are presenting a considerably lower level of inverters of THD than the competitors. We are going below 0.7%, considering the harmonic up to 190th. That means almost 10 kilohertz. How we do it? We do it by means of hardware. Our inverters have a high-tuned filter, including an additional high-frequency filter to mitigate harmonics above 50 Hz. We use also software by means of use advanced switching and control algorithms such as selective harmonic cancellation. And to prove that software and hardware are properly tuned, we perform validation campaigns, performing THD studies at high frequencies, taking into consideration up to the harmonic number 2500. So that, as you can see in the table, our converters have a real low value of THDI. We will see how this affects to the real world. We have performed a case study done by a third party, ATI, to prove that. So, that's all from my side. Thank you.
Well, Jonai has very well described the importance of harmonics. Now it's time to take a look at the numbers behind harmonics. What's the meaning of this theory, and what does it mean in terms of proper design of a power plant? In order to do that, we have considered important to rely on an expert, on a third party, on a technical advisors, in order to provide us with their view. Here the difficulty is to translate all these numbers into something that can be translated into higher production and higher revenues in a power plant. As compared to other elements of the inverter, and such as efficiency, which, as I said before, can be relatively easily simulated, harmonics is more complex. We need to run some detailed simulations using very high-level simulation tools, such as Power Factory and others. We have requested the technical advisors to analyze two cases, two examples of power plants. One in Spain, a typical 50 megawatt plant in Spain, and another one bigger, as it's the case in Australia, of around 200 megawatt. From that point onwards, the technical advisor has designed completely the plant, including not just the inverters, but also the cabling, everything from the inverter to the point of interconnection. And they have simulated these power plants. We have asked them to compare what is the difference between our inverter, the Proteus PV inverter, with other cases. We are not comparing with specific components from the market, from competition. Technical advisors has just assumed different types of harmonic content with high attenuation, a medium, and a low attenuation. Based on this, the results are very graphical. I mean, if you compare something like an ideal case with no harmonics, no losses whatsoever in the blue column, with Gamesa Electric Proteus, which is the orange in the graph, and the three cases I mentioned before with high, medium, and low attenuation. The graph shows that as compared to the low attenuation, the benefit, the increase in production is significant. For the power plant in Australia, 200 megawatts, again, the increase in production is about 0.32%. And if we go to the Spanish plant, a 50 megawatt plant, it's quite similar, even a little bit higher, 0.35. This is losses, this is a percentage. It doesn't look too high, but if we really translate that into euros, into money, this table shows that this 0.32, 0.35% can be extremely significant for the revenues of the power plant. You have here 4 different cases. Obviously, these numbers depend on the price of the electricity, of the price negotiated with the PPA, whatever the revenue stream is for the customer. But let's take a look at the lowest number in this graph. For a market price 50 megawatt per hour, which is, depending on the year, depending on the time, is something more or less high or low. I mean, today is a valid number. You see that in the Spanish case is an improvement of about 19,000 euro per year. If you take into consideration the 25, 30 years time for the whole power plant to be operative, we are talking about something which is in the range of 25% 25% of the total investment in inverters at year zero. Obviously, if you go to the highest number in the graph, which is 200 megawatt per hour, well, this is probably too high as of today, but the market is dynamic and it can change again. We are talking about something which will compensate 100% of the capital expenditure at the time of buying the inverter. So yes, this is a small percentage, but the number is extremely high and extremely relevant for the power plant. Okay, so just to conclude, combining everything we have tried to explain in this webinar. Number one, harmonics are everywhere. In the PV inverters, we cannot live without harmonics. It's intrinsic to the design of the inverters. And these harmonics generate losses, generate heat and losses. There are standards, as my colleagues has described. This standard has to be fulfilled, but the majority of the inverters are switching at a frequency which is higher than the measurement of the standard. So it's extremely important to have a PV inverter with a THD well below the limits that the standards are indicating. And this is Proteus. Proteus PV inverter is 0.7%. 0.7% as compared to the 3% that the standard is describing. So it's important, it's very important in 25 years, as I explained in this case study with the technical advisor, to really have an overall estimation of the losses during these 25 years due to the THD. That's critical, and this is an enormous impact on the LCOE. Thank you very much. Now it's time for questions, I guess.
The independent engineering report cited in the white paper mentions up to 35% difference in production between inverters with and without ultra-low THD. Enrique, to what extent the developers are aware of these figures?
Well, yes, thank you, Ayane. That's right. Developers are not really considering today harmonics. As I mentioned during my side, it's difficult to have this simulation of harmonics. There are tools to do that. I explained in the case study how developers can perform this kind of simulation. It requires some modeling, it requires some simulation, but it's not difficult. There are tools in the market to do that. It's extremely critical to do these kind of assumptions and these kind of simulations. And the key message that I would like to convey in this webinar is, for developers, it's critical for you to get the information from the inverter manufacturers about harmonics. Having this information, having this spectrum of harmonics in your hands, it allows you to do these simulations and to compare, to give a quantitative estimation of the benefits. And by doing that, you will have an overall assessment of the best inverter in terms of LCOE.
Jonai, we're seeing an increasing role of inverters, of a distributed and asynchronous network. Where do you think the technology of these devices will evolve to?
Basically, the inverters are defined by two parts. The conversion from DC to AC, which is evolving really fast because of the new technologies in terms of power electronics, going higher and higher with the frequency, the switching frequency. And on the other side, we have the advanced functionalities that are part of the grid connection. With the increment in the amount or the percentage of the inverters connected to the grid, we will need these new technologies to take a really important role in the grid. On the other side, there are the grid functionalities. We have to take into consideration that the inverter has an interface to the grid. And there, the new functionalities such as grid forming will be a vital role in the grid. Moreover, once the inverters are more and more a part of the grid, we will need the ultra-low THD as a part of the main functionality of the new inverters.
Thank you both for your presence in this webinar, and here we say goodbye, hoping it's been useful and interesting for all our viewers. Finally, we would like to remind you that the white paper is available for download on the Gamesa Electric website. Thank you very much and see you next time.